to you today, which I definitely wanted to do. I didn't have time to assess a letter grade for the test 2 scores, so you just have the number. I can tell you roughly that the scores on the test were ranging from, let's see, there were 80 points possible. They were ranging from 40 to 70. 40 to 70. So you can benchmark where your score stands in that spectrum. So anyway, I thought the first thing we would do today would be to go over some of the problems on the test, to look at that as a starter, and then we'll go back to our handout for whatever time we have left today. So let me put the solution page here on the screen. You want to hit that light for us over there, please? Thank you. How are we doing here for brightness? Okay, so here's a two-factor unbalanced problem, and here's the cell needs model, and here's the data written in column form. Input is a minitab, and then there's the minitab command. So the first question was, complete the ANOVA table below and do the test for interaction with the effects. So we noticed that I had erased some of the entries that appeared in this computer output, and you had to fill them in. So the first thing you had to do was to fill in the degrees of freedom over here. 1, 2, product 2, 13 for total because there's 14 observations in all. Then fill in the error as 8 by default. So once you get the degrees of freedom, you can divide them into the sum of the squares. And we had said in the unbalanced case like this, we should use the adjusted sums of squares, not the first one. So anyway, I look at the adjusted sums of squares, divided those by the degrees of freedom, we get those mean squares. So there's the mean squares, and then we have to form the F statistics by taking certain ratios. And which ratios are we going to take? You can look ahead down here and say, this isn't too bad because the AB is going to be 4, the error goes down. The B is going to be 4 as it's down. The A is going to be 4. So for all of the tests, we're going to use the error mean square as the denominator. And see that coming up there. So anyway, dividing these mean squares by mean square error, I get those F statistics, and then I have to go to the F table to judge significance. This one is significant, this one is not. And I forget whether this one was or was not. It looks too small to be significant. So anyway, that's the completion of the ANOVA table and the 2 tests that are in the ANOVA table. Then question B says, give a 95% confidence interval for mu bar 2 dot. So mu bar 2 dot, you can see from this definition here as to what it's going to be. And I'll write it down here on the side just for my own
recollection too. So mu r 2 dot is going to be mu 2 1 plus mu 2 2 plus mu 2 3, third column, all divided by 3. So the idea is basically for the sample estimate, we have to get a mean in, oops, that's too high. We have to get a mean in each of the 3 cells, there, and then average those 3 means. Now that's not the same as the average of the numbers across the A=2 tableau. So anyway, we need to get those 3 means. So here's the 3 means. And A is 2, 22, 16, 22.67. And then I have to take the average of those 3. So if I average those 3, I get this 20.22. Now, when I was working out for the confidence interval, the variance of this thing, I forgot the 1/9. I forgot the 1/9 from the 3 over here. So insert it on your page, because I didn't want to send it all back to the copy queue and redo the copying all over again. So on your copy, insert the 1/9 there. And then that's going to change some of the numbers that go along. And I'm not sure you need all the intermediate numbers, but there they are anyway as I changed them. So we need 1/9 from the 3 in the denominator over here. Then we need the variance of this mean, and that's sigma squared over 4. We need the variance of this mean, which is sigma squared. And then we need the variance finally of this mean, which is sigma squared over 3. And now there's just some arithmetic to put this all together to come up with the number. Sigma squared, as we saw in the question, is going to be estimated by mean square error. So I can slide that in there and calculate a final number there, and the variance of this estimate. Then for the confidence interval, I go plus or minus and look at the P table, 8 degrees of freedom coming from the mean square error, square root of the variance. And so putting in the numbers and doing the arithmetic, I come up with 4.97 for the plus or minus. So the confidence interval is the estimate plus or minus 4.97. That look okay? Yes. I'm sorry, say that a little louder, Judith.
Why don't we use weighted mean if we use weighted variance?
Why don't we use a weighted mean?
Yes.
Well, I suppose in a way we are. I mean, this mean here is a weighted mean of the original data in the second row. It's the straight mean of the 3 means, but it's a weighted mean of all the numbers that are in the second row. So you could look at it as a weighted mean if you wanted to, but I think that just complicates the situation.
focus of the parameter here says I want the average of the means in a given row. Well, that doesn't say weighted average of the means in a given row. It just says the average. So because of what's going on here, our focus is on just straight averages rather than weighted average. Does that make sense? To some degree?
Yes, it makes. I just thought that you should take, because we take at the variances too. And that's why I thought that we would take at the means. But I understand what you
Okay, fair enough.
mean.
So a little tricky about what mean are we talking about here when we want a confidence interval for this thing. That was the tricky part. And once you saw through what was needed, it's kind of an easy problem, really. There's no hard steps there. Okay. Here's a two-factor experiment. A is fixed, B is random, and here's the data, 4 by 2 in cells. So we have a question, complete the ANOVA table below and do the tests on interaction and effects. So this is the same kind of thing that came up in the first problem. We have degrees of freedom to fill out, and that's pretty straightforward. We divide the degrees of freedom into the sums of squares. There's no issue here about sequential versus adjusted because they're the same in both cases. And then we have to say, well, how do I find the F statistics? I've got to divide these B squares by something. So look ahead to here to see what the proper denominator should be for this mixed model. So if I want to test AB, the answer is clearly use 4, the error, for the denominator. If I want to test B, I've got to use AB for the denominator. And finally, if I want to test A, I've again got to use AB for the denominator. So checking these expected mean squares that came up down below, it says AB, I should use the error for the denominator. So 6 over 15 is probably the 0.41. But for testing B, I should use AB for the denominator. 29 over 6 is the F there. And for testing A, I've got to use AB again for the denominator. So 146 divided by 6.4 is a third portion of 177. So then I have to compare these F statistics to the F tables, and what are we going to get? This one is clearly going to be significant. Is this one significant? I think it is by a whisker. Yeah. And so this one is not. So we have no interaction, we have a somewhat B effect, and we have a definite A effect. And I didn't write the numbers for the table there. When I was writing this up, I didn't have the table available to me, so I left it off. Questions on that? So this was a mixed model, and we had to be careful about the denominators, right? Pedro?
Doctor, B is random and it should be divided by the error. Yes. Yes.
I'm sorry?
The factor B is random, so it should be divided by the mean square of the error, not by the interaction.
You're not gonna believe the software? You're not gonna believe this? Pardon? You think Minitab is wrong?
No, but we learned something.
We learned something different.
What'd you say?
We learned something different. You taught us that when the factor is random, we should divide it by the mean square of the error, not by the mean square of the interaction, unless B is fixed.
I said that?
Yeah.
Everybody's shaking their heads, so. So I must have. Well,
Dr. Stevens, so assuming that in your output you didn't provide the error terms using the adjusted that part of the table, then we have just used the MSC instead of the MSAB. So let's assume you didn't provide the second table.
which second table?
This one, let's assume that this one was not there, and this one was not there, and we had only this and this. Could he have used the MSE instead of MSAB? Because this one was because of this, it was very confusing. Whether we should use MSE or MSAB.
Ah. Well, you see this kind of output frequently in my handouts, right? So I was hoping you kind of know how to latch on to this to interpret it. But this term is 2, that's B. So under H naught, B is 0. So under H naught, that falls away. So if H naught is true, my expectation is that plus that. So I need some kind of derivative here. This expectation is that plus that. And there it is. So I'm not sure, Pedro, what I told you. Did I say whenever you have a random factor, you should use mean square error as the denominator? That's not right. That's contradicting many examples that we've gone through over the last several weeks.
But also that Wigner both gives support to what I mentioned to you.
Well, maybe you can show me that after class. What's your
Absolutely, I can do that.
what you're thinking of in the textbook here? Because just as a general principle, it doesn't sound right. When you have a random factor, use the error mean square as a denominator. Doesn't sound right. So show me that after class and you have a chance to look at that.
Okay.
What I'm going by is the software output here. And let that guide what I'm using for the denominators. Is there anything else I can say about that ANOVA table? Okay, so far, well, let's go on to part B of the question, which says, give a 95% confidence interval for the difference of means on factor A. So here's my scratching over here in the margin, and I think it's pretty straightforward. I get the mean when A is 2, the mean when A is 1. I take the difference, and I get here. So there's the estimate, the difference. Now I have to get my hands on the variance of this difference. Now this is an average of 8 numbers, and this is an average of 8 numbers. So the variance of the first is sigma squared over 8. The variance of the second is sigma squared over 8. And together I get sigma squared over 4. Now here we run into the issue of what am I going to use to estimate sigma squared? My choice was to use mean square AB. So if I
pull that out from over here, instead of mean square error, I use mean square AB, and I get 6.4 divided by 4, I get this from the variance, and then finally finishing off the confidence interval. I have 3 degrees of freedom because the AB has 3 degrees of freedom. And finish it off in a usual way. Now, the reason I used mean square A and B here was basically kind of soft. But basically, I'm trying to remember when I was doing the F-test, when I was testing about factor A, the denominator that I used was the AB mean square, 6.4. So I carried that idea over into the confidence interval and used mean square AB as the estimate of that sigma squared. That's kind of a weak reason, but I don't know of any stronger reason to give you than that. Well, let's come to the hard questions then. Number 3. We have 2 factors, mixed model, A is fixed, B is random. So here's the model equation. And the alphas are constants, the betas are normal, the alpha betas are normal, and the e's are normal. So it says first derive the distribution of y bar triple dot. So I start here and I say, well, just to get my fingers wet, y bar ij dot, which says average over the third subscript k, gives me something like this. Mu alpha I doesn't change, beta j doesn't change, alpha beta ij doesn't change. But I get an average coming here on the end in the e, so I have that. So I said, let's go all the way and average over I, j, and k and get this. So I'm going to pull up a mu again, but I'm going to get a 0 in place of the alpha i's because somewhere in those sums I'm summing on I, and the sum on I of the alpha i's is 0. So I drop out the alpha i's. Then when I get to the beta j's, when I sum on k, there's no effect. When I sum on I, there's no effect. But when I sum on j, I get an average. So I called it beta bar dot, averaged over the j. Then when I come to the alpha beta ij's, I'm going to get an average over both I and j. And so I called it alpha beta bar, and then I put dot dot because I'm averaged over I and I'm averaged over j. And finally, with the e on the end, I get e bar triple dot. So what kind of distribution do these pieces have? The mu is a constant, no big deal. What about this beta bar dot? Well, this is an average of the beta variables. And so its distribution is like that of a regular mean. And so I just said, there it is, normal 0, sigma squared b over b. Then I come to the alpha beta dot dots and say, what's its distribution going to be? And so again, I say normal means 0, and the variance is going to be sigma squared AB. That's the variance of the individual terms in that average from up there. And then divide by how many terms are in that average,
which is A times B. So again, using the same principle, there's the distribution of that term, and then finally the E term is normal 0 sigma squared over ABN. So I have the distribution of the three pieces. Let's combine them together, and I get this statement here for distribution. Normal being mu, and there's the variance, just adding the three variances together. And then a simple algebra step to get a common denominator gives me something that looks like this. So there's the distribution of y bar triple dot. Now, if I want to use that to get a confidence interval for mu, I start with, as you see here, y bar triple dot plus or minus t distribution point, and then square root of variance. So the square root of variance has to be this thing here. But I don't know what those sigmas are, so I have to estimate it from the data. So how do I go about doing it? I have to estimate the sum of those three pieces used down there. Well, this could be very hard if you have to figure that out from first principles. What I was looking at myself was to say, if we go back to the previous problem, which was also a mixed model, A fixed, B random, and we were looking at these expected mean squares here, there's only one of those that has three pieces in it. And the others have two. So the one that has three pieces is the one for B. And it has a sigma squared, and then a constant times sigma squared 3, which is AB, and then another constant times 2, which is sigma squared B. So it has a term for sigma squared AB, and for sigma squared B. And the constants in this example are appropriate constants to fit the size of the data. That's the data up there. It's fitting. 4 rows and 2 columns. And 2 observations per cell as well. So anyway, the hint was back here to say this mean square B has an expectation which involves 3 terms involving sigma squared AB, and sigma squared B. Now that's what I want in this problem we're looking at. I want something that has sigma squared AB, and sigma squared B in it. So that's what I wanted. And so looking back at the previous output, I said the right thing to use to estimate this numerator is right here. Well, here I wrote it. Mean square B has that expectation, just what I want. And so that's the piece that I should use in here. Now that's kind of a shortcut way to get to that answer. To figure that out from first principles is harder than I was really expecting you to do. I guess I didn't realize when I asked the question that this difficult part was going to come up. But yeah. So the easy way around it is to remember what we were looking at for the previous problem and apply that. But otherwise, if you have to work out which combination of mean squares would have that for its expectation, I'm just saying, well, that's not easy. That's more difficult than perhaps what I wanted you to do on the test with the time you had available. Although some people were doing it. I have to say. And, so that was the tricky part for number 3. how do I estimate that thing there? And I didn't give it too much weight in grading because I knew it was a tricky question. So anyway, that's what was going on. Questions? More I should say about that? Now for the real hard one, number 4, take this nested model, there it is, and somehow derive the distribution of sum of squares B nested in A. So I start with the formula sum of squares B nested within A. That's something I hope you had written down on your sheet of notes, for example, that you brought to the test with you. It's hard to remember that just off the top of your head, of course. So anyway, there's the sum of squares. Now, as I stared at this, it occurred to me that the useful approach is going to be to split this off on the side and look at the rest. So basically, I want to split off the sum on I and look at the rest and examine that, thinking of I as being some fixed row. So okay, I is fixed now as we continue. So we write down what these y bars are. Here's the first one minus the second one. And the mu's cancel, the alpha i's cancel, and I have beta ji. Now here's where a number of people fell down, in that they left it grouped as it is here. They left beta ji and the e bar ij dot together, and that isn't going to work. No, I'm sorry, I said that wrong. That is going to work. So leave those together. What doesn't work is if you group the two beta terms together, and then you group the two e terms together, and that takes you down a dead end that nothing will work out. So leave it as it is. Beta ji plus e bar ij dot, and then from the last part, beta bar dot I. Notice I left the I in there because in this whole discussion, I is just some fixed row, and then we have e bar I dot dot at the end. All right, so just to shorten the writing a little bit, call this first sum by a single letter, say xij, depends on both I and j, and then looking at what xij is, the average of that over j is what you get over here. I again is fixed. So now these xij's have this distribution. That's easy. It's an old kind of result. Normal 0, sigma squared b from the first variable plus sigma squared over n from the average in the second variable. So what we have here, looking at this whole thing in there, is that it's n sum on j of xij minus x bar I dot squared. Now, if I put in the proper denominator, which I did there, and then multiply by it in front to balance off, I can say that this variable, by our usual argument, is chi-square with degrees of freedom equal 1 less the number of variables, so that's b minus 1. So I get that far. And then I clean up the algebra a little bit in the front. So anyway, having gone through all this stuff in here, I has still been fixed in this whole discussion.
And my conclusion is that the sum on J business, accepting this constant, is chi-square with b minus 1 degrees of freedom. So now what I'm looking at is a sum on I of a bunch of chi-square b minus 1 terms. I goes 1 to a, of course. So if we add up the degrees of freedom on the sum of these chi-squares, we get, as it's written down below, degrees of freedom a times b minus 1.
You see how I had to slide this constant over to the other side, so that I was talking about just chi-square for everything alone. So sliding that over to the other side gives me this, so the quote constant in the denominator is that, n sigma squared b plus sigma squared. And we got the degrees of freedom. Okay, well, that was a hard one. I don't think anybody got it perfectly right, although a few came close. Okay, how are we doing for time? Okay, back to repeated measures designs. And the last several examples that we had talked about had two factors with repeated measures. So let me see here. On page 6, here's an example where one of the factors is the diet, the second factor is the time at which the measurement was taken. And so there's two factors, and we have repeated measurements on these subjects. Example 4, which continues on page 8, has again two factors. One is the group, which is the training program, and the other is the type of test, pre and post test. And there were 21 subjects in this experiment. There they are listed in the second column. Now, what I wanted to point out to you was that in this example on page 8, notice the model that we're using contains subjects nested in groups. In the previous example, notice the model that we used has subjects nested in diet. So, okay, that happened twice. We have nesting going on. Then we come to an example on page 10 where
we have two factors, A and B, and subjects, repeated measurements on the subjects again. And so when we did the model, we have again subjects nested in, that's A for moisture. So there's three examples where subjects were nested. Then, last time, we encountered on page 12, this example. So we had these 10 subjects, here we are in the second column, and they were getting lower high dose on drugs A and B that are recorded in the third and fourth column. So again, we have two factors, A and B, and we have repeated measurements on these subjects. Now, when we look at the model equation here, on the top of page 13, you don't see that nesting period here anymore. And that's the big deal and the point that I wanted to try to make here. So, and then we did the numbers for this example last time, as I recall. But so what I'm trying to point out to you is that we had three examples where the subject was nested in one of the factors, and then we had an example and a follow-up example where that wasn't happening. What's going on here? What's the difference? Well, I like the way the textbook talks about this issue. Let me put some of those pages up here in front of your eye. So, this is on page 294 of the textbook. It says two-factor experiments with repeated measurements on one factor. Okay? And then there's a little picture down here at the bottom which illustrates what he's talking about. So here's a layout of some data where we have factor A, which has two levels apparently. We have the subjects named in that column. And then we have the factor, I don't like this label. This should say factor B. So we've got B1, B2, and we've got B1, B2, and we've got B2, B1. So basically the columns are the different levels for factor B, but they were used in a random order, so it's not always B1, B2, B1, B2. The order was randomized on factor B. But notice in all of these, it's A1, A1. When you drop down to this level, it's A2, 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 A2. So he's saying this is an example of repeated measures on one of the factors. I guess the one factor that we're repeating the measurements on is factor B. Factor A just kind of sits here behind me by itself. So this is the kind of structure that he's thinking about for this case. Then on the next page, he writes down the model. And so we've got an overall view, then we've got a subject I nested in J. J is one of the variables. I guess it's the alpha one, like this stuff down below here. then alpha j, which is the A effect, I suppose, beta k, which is the B effect, then alpha beta jk would be the interaction between A and B. So notice the terms that are in the model here. There's subject nested in one of the factors, then there's A, B, A times B. Those are the terms that are in this model. So then there's a bunch of stuff here, rules about sums of squares, mean squares, and so forth, F statistics. Then the textbook follows with another example, which looks like that. Now that's supposed to look laid out like the previous sketch was as well. We have factor A over here at 2 levels. We have the subjects, 10 of them, and then we have factor B, which is this time period business, levels 1, 2, 3. And so we get some data. So the text shows us some plots and tries to say a thing or two about the plots. And then it gives us this Minitab output here. And it doesn't tell us the command that it used for Minitab, so we don't see the model that was inputted to Minitab, but you can guess what it is by the rows of the ANOVA table. You see we have a row for A, a row for subjects nested in A, we have a row for B, a row for A-B interaction, and then wraps up with error and so forth. So looking at the rows of the ANOVA table, you can see that they use this same model that we have just talked about back here. This one. This one. In running that Minitab output. Okay, so those are the terms that were entered into Minitab. But it makes sense, looking at the way the data is laid out here, that that's what should be done. This example, he calls it kind of a specialized example, so I guess we can skip that one here. And this is kind of a specialized example too here. What I wanted to get to was here at the bottom of page 307, where it says two-factor experiments with repeated measurements on both factors. So there's the difference from the previous case where we had repeated measurements on one factor. This is going to be repeated measurements on both factors. Well, what do they mean by this? Well, it's fairly clearly laid out here, I think, in the picture. Here. So the diagram is indicating subjects on the rows like before, and then for the layout here, instead of having factor A over here and then factor B at the top, we have both A and B in each row. So what they've done is in kind of a factorial layout, take all the four cases between the two A's and the two B's, A1, B2, A2, B2, A1, B1, and A2, B1. They're trying to indicate that there's four cases that you can see. And this is a random order. So we're trying to indicate a random order for choice of four treatments. And in the second row, we have the same four elements, but in a different order. So randomization of the order was done in the second row, and similarly in the third and the fourth. So we have both variables appearing over here, as you see. So in data with this kind of a structure, we use this model. Notice it's a different model. I don't have subjects nested in anything, right? I have a subject term, A, a B, an AB interaction, and then they add in the interaction between subjects and A and the interaction between subjects and B. Now I've seen other references where these two terms are not included in the model. So it's not universal agreement on what's the model to use for this kind of situation. We'll follow our textbook and leave those terms in the model like that. With these constraints down here on the random variables, you can see this is what we would call, which way does it go? This would be the restricted model. We've got these restrictions on the variables in the model. But be that as it may, this is the only model that our text talks about, so we'll stick with this one as far as what we're doing. So then there's some formulas in the textbook about various kinds of stuff. And there's an example that begins on page 312, where we have 12 subjects apparently, and then the treatments are these combinations between A and B. Okay. So here's the data, and then in the Minitab output, you see we have a row for subject, for A, for B, for AB interaction, subject by A interaction, subject by B interaction, and then finally the error finishing off. So it's of great interest to look at these expected mean squares that are given here, and then right ahead of it, it tells the denominator that's going to be used. So, for example, for the subject by B, the subject by A, and the AB interaction, the denominator is 7, the error, and that makes sense looking at these expected mean squares over here. When we want to test about B, the denominator should be 6, and it's got the right expected value for that. When we want to test about A, the denominator should be 5, there, and then back up to testing about subjects, the denominator should be 7, the error. So anyway, there's a nice example in the textbook. Some comments, some graphs, confidence intervals, and so forth. So I wanted to just show you the way the text was laid out. In this chapter about repeated measurements, you start with the problem where there's one factor. Repeated measures of one factor. And we go through some stuff related to that. Then they talked about having two factors in a repeated measure. where the repeated measurements were just on one of the factors. And then finally, they talked about repeated measurement designs where the repeated measurements were on both of the factors. Now, story could be made more complicated yet if one of these factors was random. You could have a mixed model. They don't talk about it in the textbook. I won't talk about it in class as well. But that would add another level of complication to the issue of what are these expected mean squares and how can we find these F ratios. Minitab will do the job right, presumably. And so that would be our crutch. We'd have a way to get the right denominators. Then we could have maybe 4 factors with repeated measurements instead of 2. Maybe in the 4 factors, 2 of them are fixed and 2 of them are random. How do you analyze such data? Well, we've got some principles that we've looked at so far that one would try to use in figuring out how do I analyze repeated measurement problems with 4 factors. So we would try to follow the same kind of principles, but it would be more complex. So I'm going to come back to our handout. There's one more example here at the end of that, page 15, and it said the problem 2716 out of Cutner. So let me find problem 2716. Put it in front of your eyes here at the moment. So it's about calculator efficiency, and the subjects are over here on the left, 6 subjects, and the columns are labeled by 2 different factors. One is the type of problem, statistical or engineering, 2 levels, and the other factor is which model of calculator, the new or the earlier, the new or the earlier. So there's factor, whatever you want to call it, A and B on the top here. And then here's the subjects labeled over here on the left. So we have repeated measurements on 2 factors here. So with the data laid out like this, I typed it into Minitab and used this command. GLM, time to do the problem, subject, problem, model calculator, problem by model, and an interaction, subject by problem, and this ampersand sign at the end of the line is Minitab's continuation symbol. So it just says the line continues on the next row. So anyway, the detail that's being specified here is y equals, let's call it S for subject. Subject, problem is factor A, model of calculator is factor B, then we have A times B interaction. Then we have subject by problem, which would be S times A interaction. And then continuing, we have S times B interaction. So notice here in the model that I'm using for Minitab, it's the second of our models. We have 2 factors in a repeated measurement design, where we have repeated measurements on both of the factors at the same time. So there's no nesting stuff going on in this line. So anyway, what do we get for the output? We have rows in the ANOVA table for those terms that I put in the model. So you see that.
And if you're judging significance just on the p-values, you'd say there's no interaction subject by model, subject by problem. But we do have significant interaction there, two significant main effects there. And the test about subject is one of the pseudo-F tests because of the X that you see there. And there's some detail below about how it formed that F statistic. So let's look below a little bit and see what we got. That's normal, that's normal. Here's our expected mean squares. So again, you need to visualize these expected mean squares as far as what would be an appropriate denominator. And the one which has no answer is the one for subject. That's got too many pieces in it. There's no single expected mean square below which will work for that. But it tells us on the next page what it did actually. It said for the denominators, starting at the bottom, 7, 7, 7, then 6, then 5, and then for the hard one, 5 plus 6 minus 7. Apparently, if you go back to the expected mean square column on the previous page and piece together those elements, you would get what we need for the expected mean square for subjects. And you can further notice the error degrees of freedom. 3.32 is not an integer, but it's using the Satterthwaite approximation there. And you've got that many degrees of freedom. So the point of this example was to notice the type of data. Notice that we have repeated measurements on both factors, and then notice what kind of model we entered into Minitab to get the ANOVA table. Once you get the ANOVA table, and then Minitab gives you the expected mean squares as well, you can finish off the problem in a simple way, in your usual way, I should say. So no big deal there. I put some plots on this example. When we were doing the testing, this is the AB interaction plot. We found there was a significant AB interaction. So there's a picture of it. These two lines are not parallel. And we can explore the differences and so forth if we wanted to. This is the interaction between, gosh, this is hard to read here, subject and one of the factors, I think it's this problem. So here's the interaction between subject and factor 8, say. It looks like this. Well, the formal test was not significant. So look at this plot and say, it looks fairly parallel. I don't see any troubles. Looks like there's no interaction between the subject and that factor. And then here's the same plot for subject versus the other factor, and it's this kind of a plot here. And again, this looks fairly parallel as you go along. And our formal test said not significant. No significant interaction between those variables. So these plots, the three of them, sort of substantiate the results of the official hypothesis test back in the ANOVA table. Well, that's the end of the handout, so let's stop there for today. And